and applied CAX. So as you guys know, I keep these things on track, and I try to move it along. This is not a lot of razzle-dazzle. This is technical. I think most everybody gets enough marketing in their life to keep them busy. So I'm going to jump in. One of the things I try to do in all these presentations, besides technical content, to show a little usability in Femap. So when I start up Femap, let's just show what happens. My screen probably looks a little bit different than your guys' screen. I have messages suppressed down there, but the color and the shading, that's all a view setting. And you think of these views, they're like databases that control everything. And I have it named Predictive Engineering, and I save it, View Visibility. I save it under Save View. And I keep lots of views around for various means. And so when I load Femap, it knows to fetch that view. And that's under Preferences and under Views. And it knows Startup View right there. Another thing I do that's hidden, I've talked about this in 10.2, but I do a lot of cut and pasting for engineering reports. So this is something new in 10.2, is that it will scale your resolution on your screen by whatever factor you would like, factor 2 or factor 4. So what this does is that when you make a resolution, when you make an image copy picture, it will take whatever on your screen and enhance the resolution. So if your screen is 1900 by 1080, it's going to bump it up. I have it set to a factor of 4. So you get beautiful high-res graphics to paste into your engineering reports. Okay, so there's a bit of background. What are we going to do today? We're going to do stress visualization. We're going to talk about how Femap manages it. We're going to go through the basic element types, solid plate beams, and validation. And the concept, if it looks good, it is good. It's one of my favorite little sayings about meshing isoparametric elements. And this got started because it's a little bit of an insider joke about whenever you see a stress contour plot, just assume that it's wrong. And it's true. I've remarked to people that all models are wrong, except some models are more wrong than others. And it's true. It's a model. It's an idealization of an engineered system. And the accuracy of the model is only good as what's going in. Your loads, more loads. I like to say there's 4 things that you have to get right in a model for accuracy. It's loads, constraints, dimensions, and mass or weight. But saying all that, one of the things people get hung up on is visualization of results. They look at a contour plot, they go, what does it mean and what's going on? So I'm going to talk about that. But before we get into the simple stuff, I'm going to drag you guys back through a little very boring but very useful mechanics. I'm going to keep it real simple. For you guys that are clients of Applied CAX through Predictive Engineering, you're available to download my course notes for FE. And it has all these AVI files and background and very on. Sum of forces. Classic, all FEA, F equals KU. We're always solving for displacements. And this K term, the stiffness matrix, that's what we want to dig into. How do we assemble this stiffness matrix, and how does it all really work? So this just sort of walks through the basic FE process and what's going on with the spring and wiping out constraints. And I'm spinning through it. It's just background. And it shows you on the notes that you talk a little theory, and then you go in and you do an actual example file, and there's a movie file to follow along with it. So you can download the AVI files and everything, and it gives you basic workflow. And my pet little peeve, read the manual. Great stuff in the manuals. Okay, I'm going to get to the visualization. Ta-da, ta-da, ta-da. Isoparametric elements. The majority of modelers out there, we're meshing plates, we're meshing solids. And then, of course, there's a few that are doing beams. And beams are exact. I'm backing up. Beams are exact because they're using exact formulation in 2D. Everything else, isoparametric elements, It's always a punt. There's tons of approximations that go in to capture the stiffness matrix of a structure because it's a finite element, and you're breaking up your structure into these finite elements to capture the deformation response. And that's done for surfaces and solids via the isoparametric element. And the reason they call it isoparametric is that it calculates the displacement within the element by a shape function based on the corner points. This is this uxi. And likewise, you can calculate any place inside the element based on your shape function, based on the corner point locations. So the concept isoparametric elements is using the same shape function to map displacements within the element and to map locations within the element. And there's a lot of little tricks. You notice on this diagram, we don't care about the global coordinate system, the element sitting off in space at x equals 0.3, and another coordinate is x equals 0.5. None of that. In the finite element process, you throw away all reality, and it's all idealized into normalized into a -1, +1 coordinate system on both axes. And that's how shape functions are dealt with in this normalized coordinate system. So for isoparametric elements, you have to go through the process, and you're talking about sum of force 0. You're developing your strain matrix, and then you relate, and this is a simple 2D. Relating your displacement, here's your shape functions. I know this seems boring. I'm going to get to the point here. And then you back it out where you're in a force down here, relate force to stress. Force is your elastic modulus times your strain matrix times change in area. Now, this is the killer page. And you really don't have to, it's just to grasp the concept that in the finite element process, we're generating a stiffness matrix to calculate. You take the stiffness matrix, you decompose it, you apply the forces, and that's how you extract displacements at the nodes. And these displacements are then used to calculate strains that are then used to calculate stresses within an element. And this is all going to make sense in a few minutes, where this all ties together. But for now, let's just go along with the flow that you're generating your stiffness matrix, your K, based on your strain displacement matrix, elastic matrix, blah, 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 dx, dy. And this is just in the global coordinate system. And it's a mess. Numerically, this is very difficult to solve. So what they decided many, many years ago is that let's go ahead and normalize it into the -1, +1 coordinate system. And this normalization matrix is going to be a Jacobian. Right there. That's the term J. And for you guys who have been out there in the FE world, you've probably seen the Jacobian bantered about, wondered maybe exactly what it is, what it's doing. All it is, it's a transformation matrix. It's a linear transformation matrix. Think of what's a transformation matrix? It's like, okay, y equals a times x. A is your transformation matrix for one scalar. So if A is 2 and x is 1, then your y is 2. If A is 3, then your y is 3. Given the value of x is 1. So it's just a transformation matrix, and it tells you how much work it has to do to transform from dx dy into this normalized coordinate system. So a Jacobian is a very good indicator of the quality of your element, how regular it is by -1 to -1. So if you had an element that was perfectly rectangular for 2D, and if you're in 3D for a brick, it'd be 1 by 1 by 1. And the same analogy goes to a tetrahedral. It would be 1 by 1 by 1. If your element is perfectly 1 by 1 for 2D, then your Jacobian is 1. It doesn't have to do any work. It's done. Oh, excuse me. Sorry about this. Your Jacobian is 0 because the Jacobian doesn't have to do any work. If your element is perfectly rectangular, I mean, it's just the God's gift to absolutely perfect. I can't even draw anything like that. And it maps, and therefore it can map perfectly to -1, +1. Then, of course, the Jacobian is going to be 0 because it doesn't have to do any work. It's not needed. Okay, let's go back to normal non-drawing. Okay. So that's one thing about the Jacobian. I'm going to tie this all together. Now, we have to do the numerical integration to extract our stiffness terms. And if we had to use something like Simpson's rule, which we might have seen back in some numerical techniques many years ago, it would take hundreds, maybe thousands of operations to map out the area for a 2D element. For a 3D, several thousands to map out the area. They've dispensed with all that, and they use a trick called Gaussian integration to map in 2D just the simple quadrants. It's down to 4 points. And these are weighted points, and these weighted points use a shape function, a normalized shape function based on -1, +1, to map out the stiffness, map out the area of this using the Gaussian integration. And then this Gaussian integration allows you to, I'll back up, allows you to calculate your stiffness and generate your terms for K. Here's an example of Gaussian integration points in regular elements for triangle, quadrilateral, tetrahedron, hexahedron, pentahedron. We call these bricks or prisms. Plate, tet. But you notice in this perfect world how even everything looks, how perfect. If you really have elements that are like this, you get perfect calculation of the area. If you have elements like this, they're 1 by 1, or you get perfect calculation of the volume. Therefore, when you have perfect calculation of the volume, you get a perfect calculation of the stiffness term. And so your element is as accurate as possible, and it does a great job. Okay. So then I talk about plate elements and so on and so forth. What I don't talk about here, and I'm about finished, is that when you're done with the FE process, I want to back up, and you have it'll dump out. Hope you guys aren't getting dizzy. It will dump out your displacements here. It decomposes K, dumps out your displacements. Now, these displacements are at the corner points. They're at the nodes. So what it does is it goes back and uses your isoparametric formulation with your displacements right here. You didn't think you were going to have a college lecture today, did you? Your displacements here at the corner nodes, corner nodes, are then mapped out to interior locations. And these interior locations are the Gaussian integration points where strains are calculated. And when these strains are calculated, they're calculated at the Gauss points, then it's real easy. Linear elastic material, Hooke's law, you have your strains, you bump out your stresses. Boom, you have your stresses at the Gauss points. So isoparametric elements, you're using your shape function all the way. You're using your shape function to calculate the Jacobian, you're using it to calculate the Gauss points and also to calculate the area or the volume, and then it's used to calculate the stiffness terms, and then it goes back out, calculates your displacements here, and then it goes back in and uses it once more to calculate your strains and your stresses. So your quality of your elements, the closer they are to 1 by 1 for a plate, closer to 1 by 1 by 1 for a TET, the whole process benefits. You get better area, better volume. You get better stresses because it goes back and forth. So one of the things that we can tie this to is visually, you know if it looks regular, it looks regular. But numerically sometimes, as engineers, we'd like to have something better than just, what do we hang our hat on? Let me erase this. What can we hang our hat on that's more concrete, more fixed? We can hang our hat on the Jacobian as an idea to assess the quality of the element and what that means all downstream. So I made a cute little, I have a little technical paper coming out on stress visualization and desktop engineering, and so I had to make graphics, and so I made this little graphic showing the Gauss integration points in Femap. I have no CAD tool. I have no graphics tool. So to give you an idea of how in the perfect world the Gauss points would be sitting, what would be happening. So, okay, so that is the theoretical background on everything. So now let's jump forward and go into let's show something that's obvious, and you guys will roll your eyes and go, yeah, everyone knows this, but it never hurts to have a little background. So here we have a domed hemisphere with some meshing that doesn't look so bad. And your eye can pick this out. Your eye looks at this and it just looks pleasing. It's regular, not so bad. And then you look at this and you got to shake your head going, this can't be good. And you just look and you just wonder, how is Gaussian integration going to put points in for something that's so distorted, element quality? And you think about it, has to place low Gaussian integration points, and it has to break it up, and you have these triangles here, and you just know that can't be the best mesh. Well, in Femap v10, you have model data contour, and it's up there. And I've talked about this before in the 10.2 introduction, show model contour. And you can do all sorts of things. If you have a complicated model, you can contour plate element thickness or other properties. But what I'm going to use it for here in this seminar is you can do element quality. Heck, you can even do explicit time step if you're doing explicit work in LS-DYNA. But there's our Jacobian, and we can contour the Jacobian over the model. And we have a range of near 0. And you go, what would be a 0 Jacobian? Well, check out that element. That's a 0 Jacobian. Perfect, 1 by 1. And then everything sort of degrades. And, it's picking up this little fan here. But it's not bad. It's around 0.5. And one of the things that you'll see, if you go to Tools, check element quality. And let's just pick a couple elements right there. That the Femap guys give you some suggested tolerances here. And one of their tolerances for Jacobian is 0.6. And I have no idea where they arrived at that 0.6, and I've asked them that. But actually, 0.6 ain't bad. You can see some of these elements here as they get up near the red, what 0.6 means. And you look at this element right here, and you go, try to break that into a -1, +1 quad, give it up. I mean, you just know some bad things are going to happen with that element. And these other elements being so large and short and triangular, you just got to believe something is not good. So, but let's turn that off. And I just threw some stresses on it. And we can go into post-processing and contour. And we can say contour right there, like that. And now the legend is scaling from 5 to 280. And what we would like to do is go into levels, and let's not do auto. Let's do max min, like that. So I've already bracketed it from 200. And now you can see the problem jumps out is that that is bogus. That's not correct. That can't exist. And can this really exist with a big, no. And you look over here, and you go, that's the way it should look. Beautiful, smooth, continuous. It looks good. It's pleasing. You look here. You just, how would you say, you don't need a Jacobian to tell you it's cooked. Okay, let's go and jump up and go do something with really bad. And first of all, would anybody in their right mind mesh a pressure vessel with Tetes? No. I did this because it gave such a good example, and I didn't have anything else I could show at the time. So I'm going to go back to here, model data, and let's go to Jacobian. And it's all pretty bad. Look at the lowest value is 0.668 at blue, and we got some near 1 that are just totally bad elements. But in general, all these elements in through there, not good. You know, you can look at the yellow and say it's around 0.8. And if we look at what it does for our stresses, nope, I want to go not deformed, contour, down there. Okay. Oh, you can see I got to turn off this. It can only do one at a time. There we go. Splotches. And again, it wouldn't need to be a rocket science to know something's wrong when you see the splotches like that. It's not a logical stress phenomenon. Stress is continuous through a structure. It wants to flow. It wants to be smooth and harmonious. But I have seen this with Tetes more often than I like to admit on doing fillets and other things. And the reason why Tetes can be dangerous and sneaky is that you got to remember the Gaussian integration points on those poor little elements. Just try to figure how in the heck you're going to get one by one by one normalization on an element like that. I mean, just think where the Gaussian integration points would be, about where it's calculating stresses and how it's doing things. And I have some more I want to add on to it, but you can just look at that. And now that you know how element stiffness terms are created, that it uses a normalized coordinate system and a Gaussian integration, you just would look at this and go, how in the heck it would get one by one out of that. And these are powerful, simple tools you can use to, because I get people ask, how do I know it's any good? And well, if I have confidence in the loads and everything else, you know, the first order stuff, loads, constraints, dimensions, you know, you're building in inches and somewhere it gets turned into meters, and masses, you know, the weight of the structure. If you get the big stuff done and you can just look at the mesh, you can look at the regularity and know it's okay, because you know how things are computed, the background. You know what's in the black box. So you look at this, and with the lower you're at 0.7, blue is 0.4, but now you're much closer to 0.6. You know, what I still, again, this is an example. I'd never measure pressure vessel using Tetes because the elements are just crap. But look at what happens when you look at stresses. Contour. Oh, I did it again. I got to turn that off. You know, it's not embarrassing. I mean, actually, in a bench, it would work. But you see, you damn well know that stresses can't fade in and out like that. And why do you get these weird colors there? I mean, why wouldn't it be, you know, uniform? Well, we know the elements are variable, they're small. And we know now that stresses are calculated at the Gauss integration points. And that's where I use this little bullet item, is that stresses are at the Gauss points. And then what happens, the last little step before a solver kicks out stresses, is it takes the stresses at the Gauss points, and this is all solvers. All solvers that use isoparametric elements, is that it will go ahead and take the stresses at the Gauss points. It interpolates to the centroid, down to here, and then it extrapolates from the Gauss points out to the node points. And this is for each element. Each element is an island. So, for example, if we just say the stress in the x direction, that component, each element will have 5 components in the x direction. It will have the x stress at the nodes and the x stress at the centroid. And what Femap is doing, and other standards, is that it's averaging the stresses at the nodes. It's taking each element, the nodal stresses, and averaging it. And I'm going to go into View Select. And people have seen this, and I know. They go, what's this? Well, that stress there, these stresses are the stresses at the centroid of the element, because it tells you the type of element, tells you the maximum, and these are at the centroid, whether it be a plate or be a solid. And the contour option, I think you guys are probably going to get this now, that what's going on data conversion, remember each element is an island. It contains its own set of stresses. So then the question is, how do we average them? And the default, I can't tell you, when in doubt, hit OK. Don't touch the defaults unless you know where you're going. But the default, it's averaging all the nodes on the corners together, and then it's contouring them like that. So if your Gauss points are widely divergent, you can imagine the stresses that is calculated at the nodes are different. So you get this variation going on that's illogical. So that is the solids. Okay, I beat up enough on mesh quality, Gauss points. I am going to get to, I want to show you, so you guys don't lose too much interest. I am going to close and talk about post-processing all the element types. But before I get there, I want to do a little bit side point. I'm going to import some geometry. I call this one good enough is good enough. I use this in the class. This is a real engineering example of something that I did many years ago. I do completely different. So this is a little surgical anvil using for endoscopic surgery. And it is teeny. If we use the measuring tool, and I'm going to snap between points, I'll snap to point and say, okay, how big is this? Just from there? And I can double click and say, and this is it when you have, let me bring up messages. It's 0.28 inches, quarter inch. It's a small little tool. And it's surgical anvil, stainless steel staples go here. And it's used to grab a vein, and the surgeon staples it shut. This is an anvil, and so the stainless titanium staple comes down here, and it bends up and staples the vein short, so this grabs it. And they were having a problem with this device. It was breaking. And they figured, let's do a stress analysis. So let's jump in. We're going to do a quick little stress analysis, and I'm going to show a little different workflow. I'm going to go for the tree, so straight Tet mesh, and it's just a linear elastic analysis. I'm going to use steel, and I'm letting it do all the defaults. When in doubt, do the defaults. And it comes back, makes a mesh. In the far lower corner, I got 39,571 nodes. Now I'm going to go up to view visibility. I don't need the geometry anymore. I'll turn off the nodes. And it looks prettier. Now, I'm going to use the selector. Guys that have been with me know it's my little favorite little shortcut. And I'm going to pick this. I have it turned to surfaces. So the selector is looking for surfaces. And it says, I want that surface right there to apply a load. And I left click, and now right click. And I'm going to go to load. And I'm going to call it 40-pound force X direction. And now I'm going to apply 40 pounds in the positive X direction going down. There's my force. Now the selector is still in surface mode. And now let's pick right here. And I'm right-clicking, and I'm going to constrain it. Fixed in. Okay. Now I've meshed. I applied loads. Let's analyze. Analyze, manage, new. And I've been doing some steady-state thermal, and I want to do static. That. And one of the things I'll edit is I'm going to go in here and turn off this. This is the print, the grid point singularity thing. And I don't want to get into it, but I turn that off because it makes the FL6 file smaller. If it looks like you have questions, you can call me later. I'm going to go previous. And I'm going to turn on the iterative solver because we're using 10-node tetrahedrals. And these are some of the little details I've covered in the past. And so it fires up. What it's doing is it'll write out the nodes and elements into a Nastran deck. I'm going to turn the selector off. And it writes it out as a Nastran deck. Then it fires up the Nastran solver. And it's going through the solver convergence. And it's done. And you can go through here. And one of the things I always recommend is look at the old load going in, 40 pounds. SBC force, load going out, 40 pounds. Looks good. Okay. We do have a result set. Post-processing. Deformed. 1-to-1. Contour. And output set 1, output vector. Because what I have is, I'm going to the list. I have some old things set up. So I want to contour the solid von Mises, like that. And contour additional vector output set. Transform. I'm still a little bit old school. I haven't picked a case. And also you can tell, I don't practice these things to absurdum. I try to keep them as live as possible. So this has come back. Now it's the results. And we have 153,000. And if we were to look at this model, knowing what we know now about elements and stresses, and I'm going to go to the selector and I'm going to turn it on element so I can interrogate. You look in the lower left-hand corner. It's reading off the elements. And I'll undock it so you guys can see this a little better. And I'm going to hold the Alt key down and right-click to bring up this menu to go pick front. And there's that element right there. And you can see in the left-hand corner, you have the centroidal stress. I'll try not to stop moving it. You have the centroidal stress of 112. And then you have the elements corner point. Nodal, you know, their average stresses at the node points from across elements, and they give you 75,000 to 152,000. And that's a big leap. That tells you that element, and that one element there, it's going all the way from 73,000 to 152. And the centroid is 112. So you might, I mean, the element is doing a lot of work to capture that gradient. And that's one of the things you look for, is how much work the element has to do. But I really prefer to keep it simpler, and I look at the element shape, and if it looks pretty close to 1 by 1, I mean that element there, or how would you say 1 by 2 by 1, or 0.5 by 2, there's reasonable limits, but it looks pretty regular. And then I look at the contours, and it looks pretty smooth. It doesn't look too jaggy. You would say the stresses, they're pretty reasonable, 10, 15% close. But my real question, I always go, what is the appropriate level of accuracy that you need out of your model before we start running around and remeshing and doing all the, you know, no, we'll up the mesh density and get a better result. This is 153. What is reality? Well, reality is maybe 170, maybe at most 170. But is it 140? No. Is it 200? No. So our answer, we can look at this knowing what we know about Gaussian integration, Jacobian, so on and so forth. I'm going to redock this. And let's, just for jokes, let's look at the Jacobian. I haven't done that in this model. Knowing that, oh, look at that. I mean, look at that element right there. I mean, it has a Jacobian way down around 0.4, 0.5. It is a very nice, but we sort of knew that just looking at the element. It's a nice element. But knowing what we know now, we could say the results are well bracketed. But one of the key things is, what sort of accuracy do we really need for our analysis project? Well, this material was a stainless steel with a yield of 100,000 psi, more or less. So anything over 100,000 psi, the thing is gone. It's toast. It's going to start to yield and break. We're at 150. The design is kaput. It's done. We don't need to remesh, don't need to do anything. It's good enough. How much confidence? We have more than enough confidence to know that it's over 100,000. Stop. We're done. And that's some of the power of the visualization, is just knowing where everything is sitting and what's happening and how to interpret the results. And also use your engineering judgment. Where's the end game on this? Where is this all going? And this is a project I've done early days. And we remeshed this. And, we did all this additional design work, and it was all hopeless. What was really going on is that this thing, the 40-pound load, that was something that was being done in quality control. They want this after this was done by powder metallurgy. After it comes out of the oven, they wanted to make sure it wouldn't break in use. And so someone had decided that, well, we want to use 40 pounds because that ultimate load, and if it survives that 40-pound load, we can go ahead and sterilize it and ship it to the surgeon. Well, what they were doing, they were pre-cracking these things. They would break them occasionally in the 40 pounds, but they survived. They actually were pre-cracking them, and of course it would go to the surgeon, and as soon as he hits it with a stapling load, this tip would break off inside the patient. Not a good outcome. At the end of the day, what did they do? Well, they remeasured everything, did some experimental work, and determined that the stapling load was around 10 pounds, not 40. The stapling load was 10. So then they said, well, let's just use 15 pounds for our QC load. And since it's a linear static analysis, you can scale the loads. So 15 over 40 is about 40%. And so you can, instead of being 150, you're down to like 80,000, 70 to 80,000, which is below the yield, part survives. You're all good to go. So, okay, now let's just do comparison element types. So I'm closing out. We've been at this 37 minutes, and I'm going to close this out in another 8 minutes because this is pretty simple. So I have 4 element types, and I have the shape turned on. And if I turn off the shape, thickness cross-section, you can see we have some plates, some Tetes, in double rolled, and some other just very, very single. And if we go into deformity contour data and do plate to top there, we're seeing the double-sided plate contour. And I want to do this a little simple. Let me turn on the thickness, okay? And right now we're doing the von Mises. Okay? And what I want to do is I want to jack up the deformation a little bit. Output set, style. And I'm new to this actual deformation. Yep. I don't use this a lot. I'm trying to use it more. So there's 10, deformation. And we're doing, at this stage, what we're showing here is the von Mises stress. So it's going to be in simple bending. It's going to be the same. So let's plot max prin. So that'll be the tension on 1. Oh, I did solid. Oops. I want plate. Come back up there. Plate, major prin. So that's the principal stress. So that is what we would expect for plate element. Tension on the bottom, compression on the top, top and bottom, plate element. Because on plates, you're going to have 2 stress components. Then if we switch it around and say, I don't want to do plates, I want to do solid von Mises, like that. And it, on here, we're not contouring the plates. We're contouring the solid elements. And the reason I did this is I wanted to show what happens when you only have one element across on this. You see how you get the solid, you can't pick this up on the solid von Mises, it looks solid. And here you can pick up what you would expect to see in bending. Along the neutral axis, you have 0 stress. But even though you have one element across, you actually get pretty good stress registry under bending. You just don't get the pretty low graphic there. And remember, that's solid von Mises. So if you switch that around and go max prin, you get something that looks like that. Now, of course, I could be doing all this from here if I was more clever. See, even the experts sometimes lag in the adoption of the latest and the greatest. Isn't it amazing, even with one element, knowing what you know about Gaussian integration? You got, 4 points in there, and it's fighting. There's no central plane. It's amazing how well what you can do with a nicely shaped element. A nicely shaped isoparametric element would do such a great job. Okay. So now, let's do more. Let's go ahead and do. I'm going to set this to plate major print. Go to contour options, and it gives you, it says double, and it gives you additional. So some of you know where I'm going with this already. Solid, max print. So now we can do 3 at once. Now we can do our solid elements, and we can do our plate elements all together, all with a von Mises. But then we're left with our lonely cousin, the beam element out here. And what we can do with that, it's at this time, we can't contour everything with the von Mises. And if you guys would like to see that, please send a development request to GTAC. I've been hounding the Femap group for a lot. I think they're sick of me about, come on, let's do beams too. So maybe you guys can do that. So on beams, the equivalent to the von Mises is the maximum combined stress, like that. And if you've been working with beams, you've seen this funky little diagram, and this is so old school. And the way that I always like to show it is I'll go into post-processing, beam diagram, contour, like that. Voila. For pulse. And you can see they all line up. They all give you really good results. Well, of course, it's a demo, almost. And I'm going to close on one last thing. Advanced post, beam cross-section. And I have not prepped for this. I have no idea if this is going to work. Well, it's going to work, but it's like, yep, can I pull this off? So what I did is I want all the elements going on, and I want to do it in 1A. And, oh, I know. I keep forgetting. I got to turn off, not that. I got to turn off the thickness. And then you go into advanced post, dynamic beam cross-section, like that. Isn't that cute? And there you go. What I did is I picked a section through every beam element. I did all elements. And isn't that just crazy? That gives you the real stresses. And what's going on behind the scenes is it's actually creating a 2D profile, a 2D mesh, numerically. And it's taking the Nastran forces here, calculate. Now here is doing axial. Let's do von Mises. This is a true, oh, we can do maximum principal stress, like that. Look at that. Isn't that just, I'm always amazed. Let's do von Mises. And for complicated sections, it's exact. Very high resolution, exact. And so that's under for turning. That is for doing beam elements. And what it does is taking the forces and calculating that section. Okay. View, advanced post, beam cross-section. That is, did I cover all the bases? The Grand Slam, Gauss points, bad meshing, introduction, stress visualization. Good. That's it. And I hope you guys now feel better about stress contour plots and knowing when good enough, it's good, and how to use. For everybody, I don't have time to get into this, unfortunately. Well, you can't do it all, and I don't want to drag these things out. So, as always, if you have questions, please follow up with an email. I haven't been able to ask questions answer them during, because my other staff engineer is out of the office, and he usually handles questions during the seminars. But I look forward to any questions you may have. You can go ahead and email me at george.laird@predictiveengineering.com. I'm sure you guys on my website. Thank you for attending. I'm going to stop the recording, and all the materials you saw here will be posted to predictiveengineering.com. If not at the end of this week, at the start of next week. Have a great day. Bye-bye.